Hello, everyone. Thanks for joining us today. Uh, Today we'll be hosting Jacob, uh, an applied physics PhD student at University of Massachusetts, Boston. His focus is on introduction, statistical mechanics, and reinforcement learning. His interest is his interest lies in advancing deep reinforcement learning from several directions, typically through online value-based methods, with results on reward shaping, value function bounds, transfer learning, average reward RL, and applications to biological and quantum control. In March 2025, he'll be joining Sony AI Deep RL team as an intern, where he'll be working on average reward problem for continuing task in high dimensional video games. Jacob, you can get started. The floor is all yours.
Okay, great. Thanks. So thanks everybody for coming. I've come to a few recent talks like this one by Gautam last week, and it was really nice. So I'm happy that I found this group, and hopefully we can start some interesting discussions. Also, I can't see the chat or anything, so please feel free to shout out at any time if something's going wrong or you have a question. But besides that, I'll get right into it. Okay, so I like this slide from Gautam, so I kind of reuse as motivation. I don't have a cute squirrel video like he did, but generally I'm interested in agents that can reuse prior knowledge by some means. So I like to think about humans, about how I learn, about how other animals learn, and I think a core aspect of that is through prior knowledge. We don't just delete optimal policies and then start from scratch every day. So trying to figure out how to build in this, not necessarily continual learning, but just efficient reuse of like libraries of skills or previous knowledge is a core aspect of my research. Okay, so I'm going to try to take us on a little bit of a journey about reward shaping and its applications that I've been working on in the past few years. And this will start from a pretty foundational work by Andrew Harada and Stuart Russell back in '99 about potential-based reward shaping. So I'll kind of explain what that is and then how we extend it. I'll talk about this new dynamic shaping algorithm that we have, this extension of PBRS to a more general RL setting called maxent RL or entropy regularized RL, and some consequences there. And then I'll talk about how we were able to use these results to derive bounds on the value function, which again inspired some new clipping algorithms. Okay, so this is sort of a trajectory, and I'll try to come back here to refresh. But at the core of these different papers will be reward shaping, and that's kind of what's inspired these results. Okay, so first, what is reward shaping? And colloquially, sometimes I'll drop potential-based, and I'll just say reward shaping in the rest of the talk. But generally speaking, reward shaping is more like reward engineering. It's just some way of changing the reward function to try to make the task of learning easier. What easier means exactly isn't always clear, but maybe somehow reducing sample complexity or giving more positive samples to the agent. And as a motivating example here, we can imagine this pusher task, this robotic task where we want this puck to be placed at a certain it's a 2D position. And one reward function we could imagine is very precise. We just put like a delta function exactly at the goal and 0 reward elsewhere. And this is very precise. We get a reward exactly where we want it and 0 everywhere else, but this can be very hard to learn from, right? Because as the agent exploring, as the robot's pushing this puck around, you'll get 0 reward all the time. It's going to be a very, very rare event until suddenly you get a large reward, and you have to hopefully incorporate that and into temporal difference and keep visiting that goal again. So this could be a very hard learning problem, and you might instead suggest some other reward functions you could use, like maybe some Gaussian. You spread out this reward function around the goal position. Maybe you base it on the velocity of the puck relative to the target. And the goal of reward shaping generally is to construct more dense, maybe more abstract rewards that encode the same sorts of behaviors, optimal policies for the agent, but are easier to learn. So reward shaping, it's a very general term, but potential-based reward shaping we'll see is a very specific form of reward shaping. So what could happen if you do the wrong type of reward shaping? You can get into reward hacking. So if you give the wrong reward function to the agent, you'll get some sort of misspecification perhaps, and the agent will do something that you didn't intend to. Was there a question? Okay, I think we're good.
Oh,
yeah.
Sparse reward setting, right?
Yeah, I mean, this is for the motivation, but it could be quite general. It doesn't necessarily have to be sparse rewards. But reward shaping is usually used to make the reward function more dense, so you get rewards everywhere.
Okay.
Okay, so one very concrete example besides this robot was I think from OpenAI quite a few years back. You have this like boat racing game, and you want to finish the race in minimum time, but you also give a little bonus for getting these you can see these little green turbo blocks, and the agent is given a small reward there every time it picks up one of these blocks, but it learns rather than completing the race, it's better to keep getting these small incremental rewards by literally going in a loop and waiting for these little bonuses to respawn and continually picking them up. And that's clearly suboptimal from the perspective that we want the boat to finish the race, but that's kind of our fault for misspecifying the reward by giving too much reward for this little subtask, and the agent will then sort of hack the reward function in a way that's easy to learn, but not exactly what we intended. So then the question arises, how do we change a reward function in a way that leaves the optimal policy or optimal behavior unchanged? So that was a bit of an open question for a while, and even now some people just kind of add terms to the reward function that they think are reasonable. But this is a mathematical question that can be posed and addressed within the framework of RL. Okay, so to formulate that problem, this will be really most of the math that we see, but I think it's a nice concrete example that's simple enough that illustrates the idea of PBRS, or potential-based reward shaping. So we want to change the reward function R in an additive way that keeps all the trajectory returns unchanged. So we have an expectation of the return under some policy, some dynamics. So it's any MDP. And the return, we add this F, this function F that we want to have be very general. This will be our shaping term. And we want to figure out what forms of F are there that leave this sum unchanged. So that amounts to this thing being 0 when we add it up over a trajectory. And notice that because it's arbitrary dynamics, arbitrary policy, it really should be any trajectory should have this 0 sum. So what kind of F could we put there? This is what Adamczyk et al. Gave us in this paper below. So they put this form here, which you can see is like a discrete time gradient, but it perfectly cancels consecutive terms in a telescoping sum. So if we write this sum up here, we write all these terms, you can see that this gamma phi of S prime will be canceled by the next term with this minus sign, and then so on and so forth. So we can abstract away the math and say this form here, gamma phi of S prime minus phi of S, will be the important bit. But this math should hopefully give some intuition for why we're doing that. It's just to give like a local gradient that will be canceled out over an entire trajectory. And you do have this constant term minus phi of S 0, but we can usually absorb a constant into the reward function or have that fixed to 0. Okay. So this is the potential-based reward shaping term here. We go from any reward function, for example, that delta function we had, and we can add something like this, gamma phi of S prime minus phi of S for any phi. So phi can be any bounded function from states to real numbers. And when you add this term into the reward function, it will leave the optimal policy invariant. It will leave any suboptimal policy values invariant because of this trajectory return. And we have quite a bit of freedom, expressivity, because of this phi. It can be nonlinear, it can be whatever you want it to be, some crazy function, as long as it goes from states to reals and bounded. But then the question is, how do we choose this phi? Okay, now it's like a hyperparameter, but over function space. It's like this huge function that we have to decide just to try to make the learning objective easier. So this phi potential, as it's called, will be at the core of the following results. But this is the functional form that we'll focus on here. Was there another question? Yeah.
Yeah. So I have a question. As you just said that Your optimal policy is invariant. So,
Hmm.
what is the motivation behind doing this potential-based reward shaping?
Yeah, that's a good question. So if we go back to like this mode, if I originally just gave a reward function, which is, let's say, +1 when it passes the finish line, the agent should eventually learn to get to the goal in minimum time because of discounting. But maybe we want to tweak the reward function in a way that makes the reward not so sparse, but still gets to the finish line in the minimum time. Here, if we add some arbitrary thing, which is a turbo bonus or whatever, we can see that's clearly not going to give us the same optimal policy. I mean, this is an example. It's not getting to the finish line at all, definitely not minimum time. So the question arises, which functions are we allowed to add to the reward that still give us the same optimal policy and don't give us something like this weird behavior?
In this context, this is not our optimal policy, right? It's actually hacking the reward function, isn't it?
I guess it depends what you mean. So they trained on a reward function that included both the like a terminal cost and a turbo bonus, and this is what they get after training. So after some finite amount of time, the policy that was found was this one. Maybe it was suboptimal, but it at least led to some local minimum, maybe if that's what you're calling reward hacking. Whereas if we had potential-based reward shaping, this wouldn't be something that's incentivized. The same policies will have the same ordering in terms of returns.
Okay.
So this reward shaping term is like a mathematical way to ensure that we don't get stuck in the policy doesn't get stuck in some loop.
Local optimal.
Yeah, local minimum. Yeah. Yeah.
Right.
So it leaves the trajectory returns ranked the same in terms of policies. So it'll still, like this would be a very suboptimal policy under the get to the goal only task. But with reward shaping, this would equally be a very bad policy. And so that's why this isn't an allowed form of reward shaping.
Okay.
So if instead we wanted to, okay, good. So if we did want to encode this turbo bonus, it would have to be in this form of gamma 5s prime minus 5s. So we could say like, +1 for phi if bonus or something, if you pick up the turbo bonus. And you can do the shaping term and it will be okay. Meaning you'll get the same optimal policy of getting to the finish line at minimum time. Okay, so I also want to explain that this is more than just a change in the reward. That's how it's motivated, that's how it's derived, but there's some different angles, different perspectives that we can take on this that led us to some new algorithms. And okay, I talked about this as like a discrete time gradient. There's an interesting paper down here, calculus on MDPs. I think it's kind of underexplored, underexploited territory, and it has some pretty interesting ideas there about the geometry of this sort of function, but I won't go into that any further. So I want to focus on this one minus sign I have here, which is that potential-based reward shaping seems dependent on heuristics or some expert knowledge to choose 5s. So how do we choose this phi function? Like I said, maybe it's based on those turbo bonus things, but generally, how do we choose that? And just figuring out this 5s will lead us to some different algorithms. So first, just to give an example of what one can choose from the original paper, if we have like some 50 by 50 relatively big empty grid world, we start in the corner, we want to get to this goal. Again, it's a very sparse reward, sparse task, so it's very hard to get to this. It's a very rare event to reach this goal. But we could handcraft a potential function, which is simply the negative Manhattan distance, because this is a grid, but like a negative distance, and that would make the reward dense. So you get a reward for being anywhere, and it should make learning easier, because now, rather than it being a very rare event to get the reward, you should be getting rewards everywhere, be able to climb this gradient. But it required some input, some expert knowledge. I mean, it's not really expert, it's quite simple heuristic, but a heuristic nonetheless. And okay, so this is the figure that was added in their paper, and it's almost impossible to see those lines for me, so I took the liberty of drawing some approximation for the line. And with no shaping, you can think of this as the error. It's the steps taken to reach the goal in this 50 by 50 grid world. Without shaping and with shaping, this Manhattan function. There's obviously a stark contrast in terms of the number of episodes required to reach the goal in minimum time. So clearly the correct potential function has a big impact on shaping. And just some nice quotes that I like from this paper. It's a really nice read. They mentioned that eventually in the future might be interesting to learn this potential function, and finding a good shaping function will be a problem of increasing importance. So that's basically where I took some inspiration from. Okay, so to try to go beyond the squared world a bit, I wanted to think of those cases where you can't just use Manhattan distance. Okay, what should you use for 5S? Well, let's try to bootstrap from our prior knowledge. What does that mean if I'm just doing some online learning in one task, in one shot, and I don't have this library of solutions? Well, maybe I can use, since it's a state function, I can use my value function. That's a function of state. And Andrew et al. Suggested that a good potential function could be exactly v star of s, the optimal value function. Now, of course, you don't have that, right? That's tantamount to solving the problem without the action values, but that would be quite hard to come by without doing some work. So what's the next best thing besides v star? Well, I thought, okay, it's v hat, the approximation to v star, and this will change over time. And so now the idea that we did in this AAAI paper is to use the best estimate for v star as your potential function and keep updating the potential function over time. So eventually it'll approach v star, but it should incorporate more information, which should be useful for sparse reward tasks, and it should be increasingly better as this v hat approaches v star. Was there a question?
Just to clarify, so this approximation of the value function you have, that's being learned, but it's also being used as a part of the potential function?
Yeah. So this v hat is it's just coming from the function approximator, let's say.
Right. So initially it's going to be noisy, right? So
yeah,
wouldn't it just be like making your rewards noisy now? So where the rewards is just like very stochastic and noisy?
Yeah, that's true. So it's in the beginning and throughout it's going to be a non-stationary problem, but especially in the beginning it's going to be very noisy because who knows what this v hat thing is. And that's why I was kind of surprised at this work actually. But as v hat approaches v star, we can at least think toward the end of learning, we should get something more informative. And I think, if I have to hypothesize or conjecture, at the beginning, I'm guessing this noise is kind of inducing some sort of exploration, or maybe some biases that help, probably in exploration.
I see. Okay, thanks.
Yeah, that's a good question. It's kind of an open question, I guess, to formalize that. Okay, so a little wall of text before some experiments. But changing this potential function over time can seem tricky because of this non-stationarity. But it turns out because of the predictable nature of TD learning, we can still prove that we get a contraction in terms of the Bellman operator. You have a contraction with the shaped reward. You still get a contraction, so we get convergence as long as you rescale this value function. I'll talk about that in a second. And as Gautam kind of pointed out here, now we're bootstrapping this shaping function from the value function, and so this can induce more noise. But it turns out in the beginning this is not detrimental, and it actually becomes quite useful later on in training. So anytime you have a value-based method that has a q value or a v value and some reward function, you can plug this in. So DQN is what we used. We also have some initial experiments with TD3 and SAC showing it's possible, but it's a little trickier for continuous actions because V of S in continuous action case, you'd have to take an integral over all the action space. But we can talk about that more if there's time. Okay, so to focus on DQN, what I like about this idea is that it's just one line change of code. So here's the code. If you want to do this BSRS, you add this term to your reward function, gamma times eta. This is going to be a scale factor that maybe you need to reduce the scale of the value function for convergence, and minus V of S. So this is gamma 5S prime minus 5S, which is what Andrew et al. Said that we should do. And then we chose 5S to be our state value function. Now for us to guarantee convergence, we actually need this eta contraction or whatever rescaling to be quite a small value. And turns out that in the experiments, you can actually go far beyond this range and get much better performance than would be suggested by, for instance, this upper bound. And in all our experiments, a positive value of eta seems to work better. So you're using a positive version of the value function, which makes sense from the perspective like that Manhattan distance. We put a minus sign on the Manhattan distance to encourage a gradient going toward the goal. Okay, so let me show some Atari results here. So we ran it on the Atari suite for about, I think, 45 environments, and we have these eta values that I showed in the previous slide, and I just fine-tuned for each environment what is the value of eta that gives the best performance, and this is a log scale. So in the best case, we're seeing more than 100% advantage compared to the baseline of no shaping. And for these tasks down here where we have a negative advantage, some disadvantage, you could instead just use no shaping. So I'm only fine-tuning with respect to eta not equal to 0. So in principle, you can have a flat line here if you want to choose no shaping. But overall, across the board, I think this idea, this one line of code can improve the performance of DQN. And so in terms of the time of training and reward, for the median human score, we can see that for a fixed value of eta, the shape scale across environments, we get an improvement for positive values of eta. So this black line is a baseline, and eta is about 2, gives best performance. But this is, it's the same idea at hardware. We just use v as phi, but we just have to rescale that v, which nobody likes a hyperparameter, but it turns out that tuning this can lead to better performance in some cases. So eta around 1 or 2 is quite robust to be a good choice across many environments that we've used, not just Atari, but these grid worlds and Mujoko environments. Okay, so here's a paper with some other experiments, but I'm going to now move on to some other parts of the story. So this is also like a little pause if you wanted to ask questions about the previous slides.
I just want to know what those environments are. Are there any continuing tasks?
Well, these are all from the Atari suite. Honestly, I don't know every single game there, but I would say most of them are episodic. For example, Palm,
Okay.
like you have, you get to 21 points and the game is over. So there would be some termination condition. And all of this is in the discounted setting, which, I have this one minus done variable, so we can do both continuing and episodic tasks. But I should say much of this work actually will extend to like the average reward setting, which I'm working on quite a bit now, but I'm not showing any results for it.
And then regarding the phi of s, how did you came up with this value function? Like, is it a heuristic, or you have some theoretical guarantees for it? How did you able to choose this value function as your phi of s? Why would this be a good choice?
Okay. So on one hand, we can say, or I can say, I trust Andrew. He's a smart guy, successful guy. So maybe I should trust when he suggested that 5s to be v star of s should be a good choice. But then I realized we don't have v star. But the next best thing we have is an approximation to v star as we train the agent. And that's, in some sense, that's a heuristic because it's some specific choice of phi. But what's nice about this approach is that there's no additional input to the algorithm. We don't have to say Manhattan distance or handcraft some state-dependent function. And the theory that we have at least proves that we still have convergence for this method. And we have some ideas in DeepRL how this relates to some regularized version of algorithms, which maybe we can talk about, but that's in the full version of the paper. But I think in terms of choosing a specific phi for reduced sample complexity, that's a pretty open problem in general, because it's very task specific. There is one work, I'll have to look up the reference, but I can send that to you. Did that answer the question?
Yeah, thank you. All right.
Okay, cool. Okay, great. Any other question about this bootstrap reward shaping? Okay, I'll keep going then. So next.
So I just want to ask one more. Can you just go back?
Yeah.
So these plots are for averaged over how many seats? Like, I couldn't see the variance, how the...
Yes, sorry.
No,
This is each environment. I'm doing these eta values here, -1, 0, and so on, for 5 seeds on each one for 10 million steps. And I average across all those 10 million steps and 5 seeds.
Okay.
So I know 5 is a small number, but you'll have to be patient with my amount of compute. Like, this is basically the biggest experiment we were able to pull off. But surely 30 seeds or something would be nicer.
yeah, sure.
Okay, can't afford that right now. Okay, so if there's other questions, please chime in. But in the meantime, I'll keep pushing and talk a little bit about potential-based reward shaping in the entropy regularized case or maxent RL. And rather than using your value function that you're currently learning, there I showed that we showed that if 5s is based on prior knowledge, meaning some v star that was learned in the past, we can derive some new exact relations between value functions that have to do with transfer learning, compositionality, combining solutions, and closing a certain zero-shot gap. So let me show some of that. Okay, so this is now in the maxent RL setting, where rather than just maximizing rewards, you have an entropy bonus. So you might want to think of like soft actor critic if you're familiar with SAC, or soft Q learning. And so here's a simple example, somewhat like this maze, 50 by 50 maze. But now rather than a Manhattan distance, some heuristic for 5s, we'll use a previous solution for 5s. Okay, so it's like a continual learning setting. As you keep learning, you can keep using your old tasks as potential functions and use those to shape the reward, which should in turn speed up learning. So in this case, we have a very simple maze. The agents spawn randomly in the upper portion of the maze, and it just has to reach this orange diamond. So we first solve this task, gives us this optimal policy, and the color depicts the value function. And we'll use that value function, state value function, as the 5s. And then we'll try to solve this task, which is the same but mirrored. So now we want to go to the right over here. And if we just solve it from scratch, tabula rasa, whatever, we get this red curve. You can think of it as loss over iteration over time. But if we shape it with our prior solution here, we get a much faster convergence rate. And the reward function looks much different. It's much less sparse. So rather than just getting a reward function here, you can now see there's rewards sprinkled all around based on this value function. So even though this is kind of the opposite, it's going to the left instead of the right, it's an opposite task, it can still give a nice performance boost because you're injecting some information about the dynamics, for example. Okay, I don't know how much time I have, but if you were able to look at the full paper for this one, we're able to show that there's a relation between the reward shaping and the prior policy in entropy regularized RL. And there's some concurrent work actually at AAAI the same year. I met somebody who's doing something very similar. So this paper is also a good read for this material. Excuse me. Yeah.
So how are the value functions initialized here?
One more time.
How are the value functions initialized? Is it just random weights, or are they starting at 0?
It's robust both. I think in this experiment we did a random initialization around 0.
I see. Okay.
Yeah, and in this case we're using the solved, like a V star from an old task for the phi. But I think the initialization would be a really good question, especially in the bootstrap case in the last examples I showed. Okay, so we're able to derive this equation. This is an exact relationship between value functions in maxent RL, and it relates any two Q functions essentially. So you solve some task, as long as it's the same state action space, you solve some task, you get a Q star, and you have some other task with a Q tilde star that you want to know. You can close the gap between them, meaning have this additive correction term here, which is again an optimal value function. So what's interesting about this is that any two Q functions, for any two tasks, no matter how different they are, different rewards, different dynamics, are always related by another value function, an optimal value function. And this optimal value function, to solve it, essentially, you're just doing a reward-shaped version of the desired solution, the desired task. So it's a simple equation, but it was able to give us, we're able to extract a lot, milk a lot of results from it. So let me just show some of those here. Excuse me, getting over a little cold here. So the first thing is compositionality. So what if you don't just have one solution? What if you have many solutions to various tasks? How do you combine those to achieve maybe some good zero-shot performance, but to speed up learning in the downstream task? So I think one of the first works in this direction was from Harada et al. In 2018. So this is this pusher task. Again, if you teach an agent to go to this horizontal line and separately to this vertical line, then you might ask, okay, I have those in my data bank. Now, how do I combine those to efficiently solve a new task, which is at the intersection of these two lines? And then you can begin to think, okay, maybe we could actually start training agents to get like this independent basis of tasks. There's an interesting paper by, I think it was by Doina Precop, on this basis of skills. But if we learn these basis of skills, then maybe we can effectively recombine them downstream. And this work was one of the first to do that explicitly with a certain form of reward function. So in their case, they said this intersection here, the reward function for that could be approximated by simply averaging the distance to this orange line and the distance to this blue line, which are the reward functions for those respective tasks. And the resulting experiment here shows that, okay, so this SQL orange line and blue line is without using the prior task solutions, just training, online as a new task, tabula rasa, and the green and red lines are different versions of merging or combining or composing those old tasks. And a few years ago now, I guess we extended this work beyond this averaging of reward functions. So we showed different functional compositions work also. We tried a few different methods of combining and showed that it does robustly speed up training. Okay, so mathematically, to use that same equation again, what does compositionality look like? Well, rather than having, again, one solution, you have many solutions. So you have this set of Q stars. And now you can plug in any function that you want. This could be a function approximator, actually, where you're trying to get a functional form that does a good zero-shot approximation. And this means that you can think of some hierarchical architecture where you have these value functions that are trained with frozen weights, and then you can learn to combine them efficiently to approximate this Q tilde star. And if you can't do it exactly, well, this result tells us how to close that gap. This is, again, another value function, so you can think of some other value function that closes the gap and gives you the desired solution. So this F, you could think maybe it's done in like an offline way, and then this K star can pick up the slack in an online way. Okay, so this is the version where they have this average reward. They're averaging the reward functions for the previous tasks, and they derive some bounds on the value functions. So I think I'm running a little bit low on time, so let me skip through that bit. But I'll be happy to talk more about it later. So let me finish up with one of the more recent works, which was at RLC last year, where I was motivated not just to derive bounds on composite value functions, like from this paper by Arnoya, but how about on a Q function that you're trying to learn actively for some online task? So how about if you want bounds on Q star, the value function that you're trying to learn? Well, it turns out using this very simple equation, Q tilde equals Q plus K, it turns out you can use that to generate bounds on the desired task solution using any Q function. So the somewhat miraculous thing from this was that you can use any function over state action space. Okay, so it could be noise, could be these crazy spikes, as long as it's bounded. It's not infinite. But any function doesn't have to be an optimal Q function, doesn't even have to be a Q function. Just some function over state action space. If you do one Bellman update on that, you can use that information to generate a bound on the optimal Q values. So we're going from arbitrary, suboptimal information to information about the optimal value function. And this animation shows how actually in a bootstrapping sort of way, you can keep refining those bounds by using the new Q that you generate, right, through whatever Bellman iterations you do, and keep refining these bounds and clipping the value function down tighter and tighter, just checking if it is within these allowed bounds. And that turns out to be very, very efficient algorithm, which was kind of surprising because it's the most simple bound we could have thought of. So I'll show you some. I think I might have the actual bounds in here, but it's a little bit complicated. So I'll just show some experiments for now. And without clipping, with just standard Q-learning in this simple maze, it takes whatever, 500,000 steps or something to learn. Oh, sorry, 50,000. And with clipping, so with our bounds that are iteratively being improved because of this simple equation, we get much faster training, and we do get some speed up when you use what I'm calling baseline bounds, which is like your 1 over 1 minus gamma, R max over 1 minus gamma, R min over 1 minus gamma. That at least puts a reasonable range on the Q values. But when you use this dynamic clipping, it's a state action based bound, and it keeps refining over time. So this is true across learning rates. It actually gives a near optimal performance. This is at least when you know the model and you can do the Bellman update exactly. But what was interesting is to recover this like horizontal line of amazing performance across learning rates. You have to not do this clipping, checking within the bound violation every time you do a Bellman update. You only do Bellman updates if the clipping didn't work. So if you just do clip Bellman update, then you get this purple curve. So you do good, for low learning rates, but high learning rates because of that Bellman update, it will send the Q function off to some bad areas. But if you just clip all the time, and then anytime you can't clip because you haven't, improved your bounds, then you do the Bellman. That's the only time you do the Bellman update. That's this red line up here. Let's see if I have this other. Okay, I don't have the other curve, but there's some other like model-free versions and some deep RL experiments there. But it turns out that using this, again, a bootstrapped bound can improve the training performance by constraining the Q values within an allowed region. So the intuition would be like the Bellman update kind of pulls you closer to the fixed point. There's some fixed point and a sample sends you approximately in the direction of the fixed point. But this clipping algorithm instead like cuts off regions of value space and constrains tighter and tighter what allowed values there are. And working together by constraining and pushing toward the fixed point gives us a nice performance boost across learning rates. Okay, I'm going to conclude now, and then maybe we can just have some general discussion. And I want to emphasize that reward shaping is not just about going from sparse to dense rewards. It actually gives us a lot more information. It allows us to reuse prior knowledge efficiently. It allows us to make new ideas about bootstrapping, some new algorithms that I showed. And these potential functions that you choose are quite abundant. So it's not just these value functions that you save to the disk when you solved all these other tasks, but it could be your own value function. And maybe there's some interesting questions about this noisy initialization and so on. That's one open question. Some other open questions are, when can we guarantee these speed ups in learning? What can we say about the loops? So that was something early on we can talk about later. And these bounds, these bounds on value functions are the simplest thing that we could have thought of. They came from this Q tilde equals Q plus K. All I did was say this K is between the minimum and maximum over 1 minus gamma. So it's like some zero shot bound. And it gave quite good performance, but how can we tighten those bounds? And how can we improve bounds on sample complexity? For example, these are all underexplored ideas. So just wrapping up, I want to say thank you to, these are my co-authors at UMass Boston, at San Jose, and now Texas Tech. So thank you guys also for listening. I really appreciate it, and I hope we can have some fun conversations now. Okay, I also can't see, so I'm going to come over here now. Okay. Thanks, guys.
Right. If anyone has questions, they can unmute themselves and then they can ask. The floor is open for discussion.
Yeah. Thanks, Rahul. Thanks, Jacob. It was a really nice thought. I was thinking about the compositionality of Q functions that you were briefly talking about before. I'm not sure if you can go back
Yeah.
to that slide. But
Yeah,
I'm
of
just,
course.
if you have time, can you maybe like spend a couple of minutes talking about that? I'm just curious what you managed to do there.
Yeah, let me, I'm just thinking maybe it's more productive to share, let's say, the paper.
Oh yeah, perfect.
Let's see. Can you see, by the way? Yeah, I think so.
Yeah.
Okay, this work kind of stemmed out of the q tilde equals q plus k equation, this f of q equation. But the question is, let's suppose that we have all of these tasks that we've solved before with reward functions R1, R2, and so on. And let's then suppose we have a new task whose reward function can be expressed as some function f of those rewards, f of R1, R2, and so on. Then the question initially posed by this paper by Arnoya was, how good is the zero-shot approximation f of q, where f is the same function that you applied in the reward space, now you apply it in the value space. So they did a linear combination on rewards, and they said, okay, let's do a linear combination on q values. That should give us a decent approximation, let's say to warm start the q function, or to bound the q function, actually. So, sorry, I don't know if there's a question. But we extended this a bit by saying it's not just linear combination, it's quite general. So we gave some conditions on this function f. So for example, there's this one lemma that says if this function is convex, sublinear, and has this maximum condition, then you can generate a bound on the optimal q function with your zero-shot guess. So not only can you do a warm start, but you could also like always lower bound the value function. As the function approximate is updated, you check, does this bound ever get violated? And if so, maybe you backtrack, or you add this clipping loss to the value function.
I see. Okay, interesting. Thanks. I'll look this up.
Okay, cool. Yeah, I'll be happy to talk about that later too. It's a little bit involved, but it's an interesting. I think it's an interesting underexplored idea, how to combine previous tasks.
Right. Yeah, because I think using the value function to do that is kind of nice, because you already have these bootstrap functions that you can just continue maintaining a copy of, rather than storing all the information in a replay buffer. It seems like a more concise way to encode all the knowledge. But yeah, this is interesting. Thanks.
Yeah, that's a good point about this continuous setting. You throw away the samples, but you don't throw away the Q function, and that kind of encapsulates all of those state action pairs and rewards that you saw. So we're using that as a
So you were talking about transfer learning, right?
Yeah, sorry, I went over it a bit fast, but so I was in like this. Let me send. Let's see, I'll share the screen again. Whoops. Okay, hang on, I'm not allowed to share suddenly. That was this q tilde equals q plus k thing. So this is what I was calling transfer learning. So let's say we have this, and you can correct me if you have some other idea of transfer learning. But let's say we have a solved task here. So we know how to get to this corner of the maze, and now we want to transfer this knowledge into a new task, which has the opposite idea. So get to this other corner of the maze. And reward shaping gives us a well-principled way of reusing that knowledge and transferring that knowledge to the new task. The way that's done is through this potential function 5s. So 5s is chosen as v star for this solved task, and that makes learning much more efficient here in the new task.
Yeah. So I mean, so you mean that in this context, like your MVP doesn't change, right? It's just your reward function. If you change your reward function, your task would change, right?
Yeah. So here I'm changing the reward function from this one, which is in this corner, to this corner. You could also imagine changes in dynamics. The exact results still hold if this, as long as the state action space is changed, is unchanged. You could change dynamics and rewards.
Okay,
But,
so if I change the dynamics, I would I would sort of like do some reward shaping, which could close the gap.
Yeah, so the reward shaping would first like initialize the Q values to hopefully much better values, but also give this more dense reward signal to learn from. So let's see if I go back to this equation. So this prior solution would be like your starting guess, your warm start, and then to close the gap to the transfer to the new target task from your source task, you can learn this function that closes the gap, this K star. And the details are in the paper, but the main idea is that it itself is an optimal value function for this shaped reward, where the potential function is now V star for your solved task.
So what is this R tilde? R tilde of SA?
Yeah, sorry, that is the reward function for the new task that you care about.
Right.
For example, the reward
Right.
being in the other corner.
Yeah. So your value functions, your Q star. If you know the Q star of a particular, I mean, like some task, source task, you would like to learn. How would you like to learn Q tilde star? Right.
Yeah, that's what this equation is telling us, that you can build off of your Q star. You don't have to learn Q tilde from scratch. You can build off of it by getting this correction
Right.
term K.
Right. Makes sense. It's like, do you have simultaneous access to two domains? Are you learning? I mean, like, are you generating experience from both the tasks simultaneously, or the Q star is just learned for a source task, like on a source task, and then you're done. You throw away the samples, and then you are trying to move to Q tilde star. I mean, like, you are collecting.
Yeah, that's the setting I'm in. But I could imagine, maybe even do have some parallel rollouts on different tasks and combine them, for example, with some function F. So it doesn't just have to be one source task; it could be many, and figure out how to stitch them together, basically.
Mm-hmm. That makes sense. Okay. Right.
Okay, good.
So how do you come up with this F is the question, right?
Yeah, that's a good question. So in like this top panel here, they just posit that the reward function, they say it's a linear combination of these two, some convex combination. And then they say, let's use the same F that we did on the rewards. Let's use that on the Q values. So also take the average. But it turns out that's not the case. You could actually use any F that you want, any function. And so this could be a function approximator, some neural network. And it could be trained to try to close this gap.
Your Q function is itself is a neural network, right?
Yeah, for simplicity, I'm saying these Q stars for the fixed task, they should be fixed. Let's say frozen weights.
Okay.
Because you've already trained those tasks. Yeah. But I think, as you were saying, you could potentially collect more samples and continue updating those over time as well.
Right. Okay.
That might be interesting.
Yeah. Any more questions? We have 5 more minutes. If you guys have a few more questions, Jacob is around. I mean, if you don't want to actually ask questions right now, you can reach out to him. Like, can you share your mail ID or something?
Yeah, that would be great. If you have questions, or you just want to talk about reward shaping or anything to do with RL. Like I said, I'm working on average reward right now, which is a fun direction as well.
Yeah. So you're currently focused on average reward setting, right? So discounted reward setting would be quite different from average reward setting. So basically, your task, I mean, the problem is different.
Yeah. So there you focus more on, this continuing setting, and instead of discounting the future, every step is treated equally. And you want the average reward to be optimized rather than this exponentially discounted reward to be optimized. And there's some new algorithms emerging in that area, but it's still a very, very new field.
Yeah, I mean, I would definitely try to reach out to you because I'm sort of like working somewhere on related to transfer, as I said earlier, something related to reward shaping.
Okay, cool. Yeah, there's also this, so let me share this paper, progressive neural networks. And this is one of those ideas that you think you have some cool idea, you think it's all yours, and then you start Googling around, oh, somebody invented it a few years ago and it has 1,000 citations. So this progressive neural network is kind of this compositionality idea in deep RL, and it shows even in the Atari domain how useful this idea can be. So that's a good one for like this continual learning and compositionality.
Or someone has a question.
Yeah, so these are asked. Okay, so I'm trying to understand, but so I'm not necessarily talking about like an LLM setting with tokens, but if the user sees later or anything about anti-potential, so actually negative values can also be encoded in the potential. It doesn't necessarily just have to be some positive incentive. You could also, just like in the reward function, you can put negative signs. If there's something that were badly done later on by the user, or the user says it's badly done, you can change the potential function to reweight those states. As long as in whatever setting you have, that's like an MDP, and you have states, maybe you can think of those as your tokens. Some tokens are maybe bad, and you can assign those to have negative potential values.
All right. If you guys have no questions, we can close the session. We can thank our speaker. Thanks for joining us today. It's really interesting.
Thanks a lot. I really appreciate it.
Yeah. So thanks for the people whoever has joined the talk. Thanks, guys.